In this paper, we present a conservative occlusion culling method capable of handling 3D minus epsilon scenes, meaning scenes with low vertical complexity. We introduce a factorization of the 4D visibility problem into horizontal and vertical components, and we solve the visibility asymmetrically in each component using the graphics hardware. We begin by building a hierarchy over the model. First, we divide the 3D space into cells on a regular grid, splitting polygons that cross cell boundaries. We then build a KD tree hierarchy over the grid cells. We position the view cell inside some leaf cell. To calculate the PVS from the view cell, we traverse the scene hierarchically in a top-down front-to-back order. Using a region-to-region visibility query, we determine if the target KD cell is visible. If so, we continue to test recursively. Visible leaf cells contribute to the global occlusion, whereas geometry within hidden KD cells is culled. We will now show our array space factorization. Our horizontal parameterization is defined using two concentric squares. The top view projection of the view cell is the inner square, and we add another outer square. We define a parameter s that runs from 0 to 1 all around the inner square, and another parameter t on the outer square. Thus, a pair of st values defines a vertical plane that intersects the view cell at s and the outer square at t. We can now parameterize vertical planes that intersect the view cell by their intersection parameters s and t on the two squares. Within each plane, we solve a simpler visibility problem by maintaining the directional accumulated umbrae. For each object, we test if the umbra is contained in the accumulated umbrae. Here, the T-shaped building is the first to be tested. It is visible and its umbra initializes the accumulated directional umbrae. According to our front-to-back order, we continue to the second box-like building. As before, we build its directional umbra from the view cell. In this case, the umbra is contained within the accumulated umbrae, indicating that this building is hidden within this vertical plane. We continue to the third building. Here the umbra exceeds the accumulated umbrae from the top, marking this building as visible and augmenting the accumulated umbrae. Similarly, we continue with the remaining buildings, which are all detected to be invisible within the plane. Notice that the front-to-back order ensures that the currently tested umbra is always behind the accumulated umbrae. These umbra testing and merging operations involve simple slope comparisons, which can be implemented for all ST vertical planes in parallel using the graphics hardware. We now show the results for our random urban city model. Here we see a video taken from within the view cell while rendering only the PVS. Notice that the model contains non-2.5D buildings and floors that increase its vertical complexity to what we call 2.5D plus epsilon. We now exit the view cell to show the PVS. Some buildings contain both visible and hidden triangles. These are usually quite tall buildings where only the top floors are visible. To indicate this, we color only the potentially visible objects and we gray out the rest. Finally, we show the entire model, coloring only the PVS. The box-filled model was used to test our algorithm in a vertically more complex model. Notice that some distant geometry is visible through the cracks between the boxes. We leave the view cell to show the colored PVS. We've also tested our algorithm on a real 2.5D model of the city of Vienna. This is a video for walkthrough in the city. Here the PVS is calculated just before we enter the next view cell. We now exit the view cell to show the entire model. As before, only colored polygons are in the PVS.